So today I would like to present to you my research entitled Formulation of Border Ownership Assignment in Area V2 as an Optimization Problem. Now my research deals with the problem of occlusion. Now occlusion may not be an everyday word for you, so let me demonstrate what occlusion is and why it is important. So now you can see me over here, and I am occluding the screen over here. However, if I move back here, I am now occluded by the screen. So occlusion is basically what is in front and what is behind of an object, and it is important to know what is the order in depth of which an object is, in order to know where an object is and what an object is. Now let me proceed with the explanation. Please have a look at this image. There are two ways in which you may perceive this image. The first way is a dark square occluding a light gray background. Another way you can perceive this is a light gray window occluding a dark gray background. So these two ways that one can perceive the image is shown in these two different examples. As you can see, in the first example, the dark gray square has a larger depth order value, and it coincides with being closer to the viewer. Similarly, the light gray window has a higher depth order, and this coincides with an object being closer to the viewer. Now in these two examples, the border that we perceive here, outlined in yellow, is owned by the occluding object. So in the case of the square, dark gray square, the border here in yellow is owned by the dark gray square, and we can show this by drawing arrows towards the occluding object. And similarly, when the light gray window is perceived, this yellow border is owned by the object. In this case, the arrows point outwards. Now, does the brain actually carry out border ownership assignment, border ownership calculation? Physiological experiments have shown that there are object site selective neurons in the brain in area V2 in the visual cortex. Now some of these neurons respond strongly to an edge in its receptive field if the object is located on a specific side. Now this image represents the two different stimuli shown to the neuron, a single neuron. Now the red circle is the classical receptive field of the neuron. And as you can see, in both of these cases, the pattern inside the red circle, or the receptive field, is the same: light gray and dark gray, light gray, dark gray, light gray, dark gray. However, the whole image shown is different. Now this neuron responds strongly when the light gray square is to the left side of the neuron, of this receptive field. But if there is no object on the left side of its neuron, of this receptive field, the neuron will respond not as strong. So you can see there's a difference in response. Now this is the response shown in spikes per second. So this difference shows that there is a possibility that V2 calculates or assigns borders in the brain. Now, so the next question is, how do these neurons calculate or assign border ownership. As you can see that there are no cues inside the receptive field to calculate, which means it uses information from outside its classical receptive field in this area, for example. Now there are several models that have been presented to date to try to explain, to try to reproduce the response of these neurons. And the primary objective of these existing models is to reproduce the phenomenon or the response of these object side selective neurons. And you can group them into three different groups according to the neural, the kind of neural connections it uses. It hypothesized. Yes. And so we can group these into three different types. First, lateral connections. Second, feed forward, and third, forward feedback. I will not go into the details, but for example, for the lateral connection model, you can see that it uses very complex neural weights to calculate all the connections, the weights. So the approach that we took is different from the existing approach. Now the approach we took is a deductive approach. Now why a deductive approach? First let's start with the phenomenalistic or the inductive approach. Now this approach is, well, you start off by presenting a hypothetical neural mechanism and you work within that frame to reproduce the phenomenon or the neural, the response of the neurons. However, on the other hand, a deductive approach starts off with presenting a theory and then deriving the neural mechanisms as well as the algorithms to implement it. Now, a deductive approach has been taken previously in area V1, and this has resulted in famous theories such as the Gabor sparse coding and the Gabor function. However, in area V2, there has not been any research at all which has taken a deductive approach to solving the problem of, let's say, border ownership. So how do we approach this problem now? First, we have to define a suitable energy function for minimalization. So let us take a look at the relationship between depth order and border ownership, or BO. Now depth order, as you can see, is three-dimensional information. So we can represent this, for example, x, y, and z, as a scalar field, let's say phi. And border ownership, BO, we can represent this, you can see arrows here, we can represent this as a vector field. Let's say, for example, E. So we have phi here and we have E, and we know that there is some sort of relationship between phi and E. So what is this relationship? For example, this looks like a differentiation integration relationship. In other words, if you differentiate a scalar field, you will get a vector field, a conservative vector field, and if you integrate this conservative vector field, you will get a scalar field. And now this relationship can be expressed in this equation here. E equals to the nabla phi, and nabla is the differentiation, represent differentiation. Alright, so we have established a possible relationship. Now how do we solve the equation? For this, the previous relationship to hold true, the vector has to be a conservative field. And for a conservative field, all points all spatial points, the rotation or curl of conservative vector field has to be 0 at all spatial points. And the equation for curl can be expressed in terms of partial differentiation of its y and x components respectively. Now, to visualize the rotation or curl of a vector field, you can take a look at this small example here. Now, these arrows represent the vectors, and if you put let's say a windmill at this point, point 0, 0 here, it will rotate up to in the anti or counterclockwise direction, and this is a positive curl. So curl is not 0 at this point. So we have an equation, or we have a function which calculates rotation or curl, and we want to make sure that every point there in the vector field is 0. Every point of rotation is 0. So we formulate an energy function to minimize curl or rotation. Now, how we derive the update rule is using the steepest descent method, and we will the result is a update rule which is in terms of the x and y partial differentiation on the x and y components, which can be represented or rewrote into this one line. Now, based on this, we then created a model, and created a simple model. Now, first we had to assign initial vectors to the shape. Now, here we have two examples, two different shapes, and for initial vectors we use vectors pointing to the inside of L junctions, and this is because the inner side of the L junctions is more likely to be perceived as an object or an occluding object. But these two images look similar, but there's one difference here. This area is absent from this image. However, at this enclosure here, you can see that the vectors point in the same direction. So if we implement our model, the update rule, to this image, this image, what we get is the evolution of the border ownership signals and depth order phi. Let me play this once. As you can see, the vectors will slowly realign themselves to point towards the occluding object. And at the same time, you can see depth order will change according to how we actually perceive the object. Now let me run that one more time. First of all, these two vectors point in the same direction, but however, if you run that, in the first example, these vectors remain in the same direction. However, in the second example, the vector will realign itself. It will turn around and face this side, which is the side of the occluding object. And we can also derive neural weights from the update rule. And we use this by, this is the update rule, and we replace the spatial, partial derivatives with discrete Gaussian, the partial derivative of a discrete Gaussian function. And from that we derive neural weights. And in the next slide I will show you the neural rates of a neuron with a selectivity to the right at position 0, 0. Now our model is, the characteristics of the neural weights of our model is on the left side here. And the darker, these vectors represent the selectivity. This is the strength of the weights. Now we can use the same method to compare it with an existing model, with Lee's model, which has 23 parameters. Our model only has 1. So let's take a closer look. First let's look at the direction. You can see direction point upwards. Right, down, down, right, up. So you can see that the characteristics of the neural weights of our model and Lee's model are qualitatively similar. However, the advantage is that our model only requires 1 parameter, whereas Lee's model requires 23 parameters. Let's take a closer look at Lee's model. You can see very, very complex. 27 equations, 23 parameters. It speaks for itself. However, let's take a look at our model. Simple. 3 equations, 1 parameter. You can be the judge of which might be a better model. Now let me close off. Give a conclusion that this is the first study to approach Wallenstein assignment in Area V2 as an optimization problem. So this is how the scene was before our model was introduced into this world, and perhaps after, maybe this is the first of maybe many similar models in the future. And the advantage is that our model presents a clear mathematical objective for Area V2, which is minimizing curl. And we've also demonstrated that neural networks can be derived from this update model. So I'll leave you with this update rule, simple update rule. Thank you very much.